Welcome to Wireless Fundamentals, Session 9, RRM Data Rates and Power. Now that you understand some of the main functions of RRM, it is time to discuss RRM data rates and RF power. We'll start with a discussion of adjusting data rate settings to maximize RF performance. The rest of this session will revolve around understanding RF power, how to measure it, how to configure it, and how to assess it in a WLAN deployment. One of the least used but more effective means of improving overall WLAN performance is by managing RRM data rates. This is especially true of high-density deployments. You have learned that you have to be close to an AP to connect with high data rates. They have a small circumference around the AP. As you move further from the AP, you connect at slow data rates. They have a larger circumference. If a proper site survey was performed, then APs can be scientifically placed in an optimal location relative to other APs. A common site survey target is to determine where the -67 dBm ring is that surrounds the AP, and place other APs so that their -67 dBm ring has about a 20% overlap with its neighbors. This should be done with APs at about 40 to 60% of maximum power. With this boundary, you'll typically connect at about 24 megabits per second or faster. Even if this is done, performance is not optimized due to the default data rate settings that all manufacturers use. By default, 1 megabit per second is the slowest mandatory rate. The slowest mandatory rate is used for all management frames, such as Beacon and AC. Mandatory rates are also used for broadcast and multicast frames. So, although you ensured that users would always connect at about 24 megabits per second or faster, management and broadcast traffic is still sent at 1 megabit per second. The resultant co-channel interference is often not apparent when clients are more sparsely populated. However, as user density increases, this issue becomes ever more egregious. For this reason, it is often a good idea to disable slower speeds such as 1, 2, 5.5, 6, and 9 megabits per second. If you must support 802.11b clients, set the slowest mandatory rate to 5.5 or 11 megabits per second. The result is that all management frames are now transmitted several times faster than before. Also, since lower speeds are never used, co-channel interference is drastically reduced. If you have the advantage of a good site survey, you can confidently disable the slower speeds. If not, you might take an empirical approach. Disable 1 and 2 megabits per second and validate that user satisfaction remains consistent. Also, some devices that are not fully 802.11 compliant may refuse to connect if slower speeds are disabled. While this is the fault of the manufacturer's non-conformant implementation, you may still be required to support these devices. In this case, you must of course leave the slower speeds enabled. Like most parameters, data rates can be configured from either the GUI or CLI. From the GUI, navigate to Radio Rate, and then click on your preferred mandatory and supported rates. From the CLI, enter WLAN RRM, and then enter the .11 commands as shown. There are several concepts related to RF power, signal strength, and measurement. The power output of a transmitter and the strength of a received signal can be measured in milliwatts or in dBm. They are simply two different scales that can be used to measure the same phenomenon. This is similar to how a weight can be measured in either kilograms or pounds. RF power does not work in a linear fashion. It is logarithmic. For example, if you stand some distance x away from an AP, your signal strength will be some value y. If you stand twice as far away, your signal will not be half as strong. It will be 1/4 as strong. Milliwatts can be used to measure RF power. However, it is a linear scale being used to measure a logarithmic phenomenon. At a close distance, the client signal strength might be 0.00001 milliwatts. At some farther distance, the signal strength could be 0.0000001 milliwatts. The numbers can get pretty cumbersome. Meanwhile, dBm is a logarithmic scale used to measure a logarithmic phenomenon. dBm may seem foreign at first, but it is easier to use. That's why WLAN engineers use dBm. Hey, what's your signal strength? It is 0.00001 milliwatts. Or you could answer, it's -70 dBm. It's easier to say. You just need to understand this new system to know good from bad. Let's look at dBm as relates to typical AP transmit power. When setting or measuring AP transmit power, you should understand the rule of threes. Each 3 dBm shift represents a 50% reduction in power. If you're not used to thinking logarithmically, this is not intuitive. Let's look at some common transmit power settings for APs. 20 dBm equals 100 milliwatts, 17 dBm equals 50 milliwatts. Do you see the 3 dBm pattern now? And recall that by definition, 0 dBm equals 1 milliwatt. Say you configure an AP to transmit at 14 dBm. Remember, an omni antenna radiates in a semi-spherical pattern, so that 25 milliwatts of power is spread evenly within this large balloon-like shape. A client only receives that tiny portion of the signal that hits its antenna, a very small portion of the total AP power. The dBm rule of tens is very appropriate here. If you are very close to an AP, your endpoint may show a signal strength of -50 dBm, which equals 0.00001 milliwatts. This is excellent signal strength. A bit farther away, and you may get a -60 dBm signal. Still very good. -70 is not exciting, but usable at 0.0000001 milliwatts. Can you see that each 10 dBm shift down drops the power by 1/10? That's the rule of tens. Also shown is the common target of around -67 dBm. When doing a site survey, we set a test AP to 50% power at a particular location. Using site survey software, we walk around taking measurements to draw the -67 dBm outline for that AP onto a floor plan. We then place the next AP so its -67 dBm ring overlaps the previous by 15 to 20%. Another key value is between -95 and -100 dBm. This is considered a typical noise floor, just the noise created by each RF component itself and the general radiation present on this beautiful blue planet of ours. Wow, what a mouthful that sounds like. What is our effective isotropic radiated power, Jim? Makes me feel smart just saying it. It is actually quite simple. Effectively, how much power is being isotropically or uniformly radiated? Each country's authority sets their own legal limits on maximum EIRP, above which you are breaking the law. We needn't be too concerned about this for our purposes, though. We are doing indoor installations with HP APs with integrated antennas. Manufacturers ensure that these products are legal at maximum power. EIRP is mostly relevant when doing outdoor deployments, especially long-distance bridge shots using high-gain antennas. Here's how it works. Say you have set an AP's transmit power to 11 dBm. You've connected around 50 to 75 feet of cable to the AP with associated connectors. The resistance of the cable and connectors creates 2 dBm of loss, so we're down to 9 dBm by the time the signal reaches the antenna. This HP antenna has 8 dBi of gain. Added to the 9 dBm arriving at the antenna gives us 17 dBi of EIRP. This is well within the ETSI's 20 dBm legal limit and the FCC's 36 dBm maximum. The HP Unified WLAN solution accommodates global companies by allowing multiple country code settings. This allows APs in various countries to operate in accordance with local regulations. You set the country code of an AC during initial boot up and change it with the WLAN country code command. You must also be careful to purchase the right AP for a particular country. APs that include IL or JP in the part number are for Israel and Japan, respectively. The AM part number is for North America, and the WW part number can be configured to operate for any country except IL, JP, or AM. In the AC's CLI, you can create AP groups for different countries and set the country code as appropriate. RSSI is a common term used to discuss WLAN RF performance. Officially, the IEEE 802.11 committee defines this as an optional parameter that has a value of 0 through RSSI max, which is 255. In other words, the standards body suggests that manufacturer hardware provides some indication of signal strength to the software layer. This can be in the form of an 8-bit value, but manufacturers are free to use any range they see fit. For example, the Atheros chipset uses 0 through 128. Some symbol devices have used between 0 and 31, etc. Since the standards body did not dictate exactly how this is to be done, you must be wary of comparing RSSI values reported from different manufacturers' products. Practically speaking, the software must receive whatever value the hardware provides and convert that to something useful. For an end user, the classic 5 bars icon tells the user how strong their signal is. RF engineers need something more precise. RF software typically specifies specific wireless NICs that can be used, and so an appropriate calculation can be done to convert whatever the PHY layer reports into something usable, like dBm. The HP Unified WLAN solutions accurately measure RSSI and use the values for transmit power control and to report general AP and client RF health to the AC user interface, and to management packages such as IMC WSM.
Hey man, let's move closer to the stage. What? I can't hear you!
You could be speaking very loudly to your friend, standing right next to her. The signal is very strong, however the background noise is also very strong. When there is little difference between the signal and the noise, communication is not effective. This is like a poor SNR value. SNR is simply the difference between signal strength and noise. You just learned that a typical noise floor is around -95 dBm, which is what the AC is reporting. In that area, a client's signal strength is very good at -65 dBm. 95 minus 65 equals an SNR of 30. This is a nice, healthy value. However, you could have the same strong signal of negative 65 dBm, but in a noisy environment where the noise floor is negative 78 dBm. 78 minus 65 is only 13. This is not a good SNR value. We either need to locate and eliminate the interference or try moving the AP to a different channel. Just don't make the mistake of assuming a strong signal equals a healthy RF environment. Validate that the noise floor is low. In the GUI of an HP Unified AC, you can navigate to Summary, AP. Select an AP and then choose the Radio tab. Okay, with all you've learned in these first 9 lessons, you should have an optimized system of controllers and APs, providing good coverage and optimal client connectivity. But how do we validate this? In Session 10, you will learn about specific techniques that can be used to further enhance WLAN performance. You will also learn about various tools that are available to help you assess the current state of your WLAN systems.